All right, next up we have Darren Dehesa, who will also be going over the Rankin development.
Like Alex said, my name is Darren Dehesa, and I'll be going over the results for the Rankine cycle for Zone 2. And my group mates were Jonathan Anderson, Nicholas Russo, Steve Colomb, and myself. So I'm going to go over a quick overview of what to expect in this presentation. First, I'm going to go over the experimental equipment, and then talk about the Rankine cycle shortly. Briefly. Talk about how each component in the Rankine cycle operates and all that. We'll go into some data reduction and some graphs where we'll check out some trends from the experiment, and then do some calculations based on a specific time mark that I chose, which is 4.2 minutes, and lead into the cycle calculations from those from that specific time. So here's the apparatus we have. Right here you can see in the upper right-hand corner, this is the condenser tower. This is the boiler. That's the valve which controls the amount of steam entering the turbine. Here's the computer that we use with the Rankine cycle program. Here's the water level part on the boiler, which allowed us to read off the water level for the steady state. And here's just the instrument panel for the turbine test stand. Here's a more detailed apparatus diagram. You can see we use liquid propane as our fuel source, and what our goal was to measure the amperage and voltage and see how that was affected by the operating conditions at steady state. That's that. The Rankine cycle, to get a complete cycle, you need to have a complete loop. So this thermodynamic cycle loop is composed of 4 components: a pump, a boiler, a turbine, and a condenser. In this experiment, unfortunately, we did not have a pump which pumped water back into the boiler, but most of them do. So at the pump, you have a work in, and ideally, you want this to come out as saturated liquid in both the actual and the ideal state, because pumps don't like water in the mixture phase. And then in the boiler, you have a heat addition in, which was that liquid propane that we use, which supplied the heat to the boiler. Ideally, you want a saturated vapor coming out of the boiler, but actually, superheated vapor is better. You can get more expansion through the turbine with that. The turbine is what provides us our work out of the system. It receives the superheated steam from the turbine, from the boiler, and ideally it isentropically expands, but actually there's no isentropic expansion. It's more of, you can see right here, this is the actual irreversible one. It kind of increases in entropy here, but it still goes into the vapor dome, because it needs to go through the condenser. And then lastly, you have a condenser which removes the heat. Ideally, you want it at constant pressure, but in actuality, you have a slight pressure drop through the condenser to the pump. So going to our first graph. This shows our fuel flow rate graph, and the reason why it looks jagged like this is because of the scale. If I was to scale this in terms of from 1 to 10 possibly, it would show a very straight line. But actually, the fuel flow hovers around 5.5 liters per minute. Here's the boiler temperature graph. You can see it's very straight right here, which is represented by steady state. So steady state occurs from 2 minutes to 6 minute time. And we can see that based on all the other graphs, this would be where the steady state measurements were taken. Here's our boiler pressure graph. Again, this jagged line is actually straight if I scaled it correctly. The turbine inlet and exit pressure, you can see also very straight through the steady state values. Here's the turbine inlet and exit temperatures. You can see they hover around 104 at the outlet and 120 at the inlet. And that's in degrees Celsius. Here's the generator amperage graph. We are hovering around 0.9 amps throughout the entire steady state time. The generator graph, 6 volts, which was pretty flat, which was what they want us to stay at. And here's the generator speed, which also will remain constant from 2 to 6 minutes through steady state, right around 140, 145, I say. All right, these are specific time marks at that 4.2 minutes times. Here's the data from the steam tables that I gathered. You can see they all make a lot of sense. Here's the mass flow rate calculations. You can see we're right around 0.006 pounds per second. Here's the boiler heat flow calculations. You can see that the heat from the fuel and the heat from the boiler are practically the same. That's because it's limited by the amount of energy that is supplied by the fuel. So that's that theoretical maximum heat that can be supplied by the fuel is also related to how much heat can be achieved from the process. Here's the turbine work calculations. You can see we're at right around 0.058 BTUs per second. Here's the heat flow and efficiency calculations. We can see right here the efficiency, the thermal efficiency, I believe. Notice the condenser efficiency is around 14%. We have approximately 0.67 BTUs per second of heat rejection. Here's the generator efficiency. We're right around 9–10% generator efficiency. And here's the work produced by the turbine once again. Here's the thermal efficiency of the system. We have about 6%. And in conclusion, we can see that we were asked to evaluate the loading on the turbine. The loading is important because as you increase the load, the more work is required. And in order to have a good efficiency, you need to increase the load. If you didn't have a load, your efficiency for the generator would be absolutely terrible. And to increase the thermal efficiency, we could possibly increase the amount of heat put into the boiler, so possibly use a higher burning fuel, possibly like use hydrogen maybe. And that's it.